Hello, everybody. Welcome to today's episode of iCANX Talks. My name is Christian Nijhuis. I'm at the University of Twente, and I will be today's moderator. And this month, we have a very nice lineup of speakers again. Like always, we already had a contribution from Grizzle, from Len, and next week, Hong Soon Boon from Tsinghua University will give a contribution. But today, all attention is, of course, on Yoeri van der Burgt from the University of Eindhoven. Today, we have two panelists, Hans Kleeman and Pascalis Kupidenis. And the challenger of today is Paisang. Today's speaker, Yoeri van der Burgt. He is a professor at the University of Eindhoven, leading the group of neuromorphic engineering. He obtained his PhD in 2014, had a brief stopover at a Swiss startup before he joined as a postdoctoral fellow Stanford University. He has been visiting professor at MIT, University of Cambridge and Georgia Tech, was awarded the RC starting grant, and received quite a few awards, including the MIT Technology Review Innovators for Honor 35. He is also a member of the Scientific Advisory Board of the Center for Cognitive Systems and Materials at the University of Groningen. Well, without further ado, I would like to give the dance floor to Yoeri van der Burgt so he can give his contribution. So I will stop sharing my screen, Yoeri, and then you can take it over. So please go ahead.
Thank you, Chris, for the nice introduction, and thanks for the organizers for having me here. It's really a pleasure to give this overview of what we've been doing in our lab. So my title of the talk is Organic Neuromorphic Electronics, and we're going to try to explain what it is that means. And I put this nice image of a brain and a chip here because we're actually working at the interface of brains and chips and trying to emulate those things. Organic, we will talk about the materials, which is polymer-based organics. Neuromorphic, meaning that we are actually doing things that are brain-inspired, and electronics means that we are actually doing these things on an electronic way. Neural networks and deep learning are nowadays very much ubiquitous in daily life. For instance, we see this applications like medical diagnosis or face recognition on your phone, or even machine translation, autonomous driving. And I put this image here a couple of months ago because nowadays everybody's obviously working on ChatGPT and OpenAI and generative AI. And this is actually very nice because you can use these systems to make new things and to give you feedback on what you've written or to make images. But it also comes at a cost, right? No free lunch here. And the cost is shown a little bit here, where this graph shows that the computing power from the 1960s to the 2010s was more or less doubling using Moore's law. And at the same time, the same thing happened with artificial neural networks. So basically, AI was becoming a little bit better and better. And then at some point, you see the steep increase. And this steep increase is coming from a couple of reasons. So the reason that AI is becoming more and more prevalent is, one, there's more data that people can train their systems on. So you have a lot of things on the internet, images, but also people giving feedback or text. At the same time, there was also, they found out if they use graphical processing units, so GPUs, people could actually start making these training systems a little bit better and easier. And you see that in the modern area, things are really picking up in terms of calculation petaflops per second. But that's all very nice, and things are becoming better and better, but it comes at the cost of power consumption. And this is an image or a graph where you see the power computing energy per year, and you see that at some point we're starting to reach we're slowly approaching the world's energy production. And it's already been calculated that data centers or AI training models are becoming using more energy than some complete countries. So really, there's something going on here that we have to solve. There's just not enough energy to start making all these AI systems available. So this is another graph to show the computing power through Moore's law. So you can see here, I mean, it's already a bit old, this graph, but you can see here that it nicely follows a trend where power density and clock frequency was kind of growing until the 2010s or so. But all the way on the bottom, you see here our brain. So the human brain is running at a much lower clock frequency, and it's also using lots less energy per square or cubic centimeter. In fact, the brain is basically using around 20 watts compared with computer systems for similar tasks that can use tens of thousands of watts. So really, the brain is doing something very efficient. For instance, in pattern recognition, image recognition, recognizing, classifying things. It's much easier for us to recognize a person if they wear sunglasses or a hat, or change the lighting of a picture. While for computer systems, it used to be very difficult to do that. Now, the brain at the same time is also very complex. It's also very difficult to understand how the brain moves. If we want to use the brain as an inspiration, it's also necessary to really find out what is happening. And this image from this paper here in 2002, you can see already there's quite a few things to measure the brain, but they're all, there's two things that you can see. They're either all on the surface or near the surface of the brain. They can penetrate a little bit, and everything they measure is electrical activity. And I'll come back to that a bit later. So it's very complex to measure the brain and to understand what is happening. Still, we want to use the brain as an inspiration. Now, I'm not a neuroscientist, but people tell me that the brain works with two components. So you have, on one hand, you have the neurons, and on the other hand, you have the synapses. Now, the neurons, the white things here, are actually talking to the other neurons through this point here, which is called the synapse. And the synapse is basically the connection point between two neurons. Now, the synapse, when two neurons talk to each other very often, so a lot of signals going from one neuron to the other neuron, this strength becomes stronger and stronger. Now, if you look at the synapse, how does it work? You see that in biological synapse, you have neurotransmitters that actually penetrate from one side to the other side, and communicate through that. So if this synapse becomes closer to each other, or there's more neurotransmitter vesicles, the synaptic strength between two neurons becomes stronger. Now, this can be used as an inspiration for neuromorphic, for neural networks as well. So how does a simple neural network work? Well, I show you a simple one-layer neural network here, where you have an input. This can be any type of signal. It could be the pixels from an image or sensor data. And then you have the output. And the connections between two neurons, in this case, are represented by this arrow, and the weight of the arrow, so the strength of this arrow, determines how much of this signal is propagated to this signal. Now, this is just one neuron, and one weight, and one output neuron. But obviously, there's in a neural network, you have many of these crossing. So you have multiple inputs, all the pixels of an image, and multiple outputs, all the classifications of an image. So it could be cat or dog, etc. Now, as you can see here, I drew the arrows of these connections in a different way. So you have very thin arrows and very thick arrows. Depending on how strong or how thick this arrow is, it actually means the weight of this strength. So from this neuron to this neuron is much less strong than from this neuron to this neuron. Now you can write the mathematical equations for this. And for a neural network, for a single layer neural network, the equation of this output neuron y1 is nothing more than the input neuron x1 times w1 plus x2 times w2, etc. So you see a nice summation equation shown here, basically showing the output neurons y's. Now in hardware, this is obviously if we want to use this as an inspiration and build a hardware system from this, it's going to be very difficult to do that, right? You can see that all these crossings between these arrows, that's not something you can very easily do. So luckily, there's a system, and it's called a crossbar array, that actually nicely takes the laws of physics to use this equation in hardware. So how does it work? You should see that there's two lines here. So you have the word and the bit lines. They're crossing, and they're actually at this point not touching. So this is on a different level than this part. The only way they are connected is through this variable resistor here. And the variable resistor is going to be the one that takes care of the synaptic weight. So if you then take Ohm's law and Kirchhoff's law together, you'll get something like this. You have a voltage 1 coming in on this whole line. That is multiplied by the conduction of this weight, and then voltage 2 is multiplied by the conduction of this weight, and all the currents are summed into this Y1 here. And you can already see that Y1 is nothing more than the summation of all the voltages and all the conductances. And nicely, what you can see is that these two are obviously exactly the same. So this one is a hardware representation of this system here. So today I would like to present in this outline how we actually start to make these kind of neuromorphic systems, what materials and devices we need for that, what are the properties that we need for that. I'll show some applications that we can actually do with our devices. And I finally end with some other nice things that organic materials have, which is that they can be used at the interface with biology. So materials and devices. So we work on organic materials, and organics are basically polymers in our case. And there can also be small molecules, but we work on organic polymers. And I highlight a few examples also from our panelists today, where organics can actually be nicely used. So I'll highlight the in-memory computing, but there's also other things like Pascalis has shown where basically a lot of devices emerge in a electrolyte can actually have global oscillations talking to each other. Hans Kleeman has nicely shown that you can do reservoir computing with these p-dot polymers, and I'll show also that we can do some autonomous robots here. But what is it that organic mixed ion electron conductors are actually? So like I said, we work with polymers. So in our case, polymers are semi or conducting polymers like p-dot PSS. And the idea is that these polymers have this thiophene backbone where holes can run around. So basically, this is a conducting backbone. Now, if you add some kind of a hydrophilic element like the ethylene glycol chain here, you can make sure that this can be soaked into water. And if you have a certain morphology, then the water with the ions can actually penetrate these systems nicely. So this is a general overview of the polymer, how it's structured in morphology and in polymer rich and in p-dot or PSS rich regions, and this works very well. But obviously, there's other types of polymers, and this is a nice review paper that you can find if you want to know more about how these polymers are actually made. But basically, the idea is that you have to have some kind of conducting or semiconducting backbone, and you have to have some kind of side chains that make sure that the ions can actually penetrate. So then the devices itself. So I guess everyone is familiar with the field effect transistor, where you have a certain channel, and this channel can, if you put a voltage on the gate electrode, you have a dielectric, you basically start to attract mobile charges to the interface, and you get a nice little interface that conducts the current. You can do the same, but instead of a dielectric, you use an electrolyte. You still get a single double layer at the end, the interface to make the current go. Now, in our case, what we do is actually we use this mixed conducting polymer, as I showed you in the previous slide, where basically the channel can be fully soaked with electrolyte and ions. So you can already see that for each of these ions, the green ions that go into this channel, a positive hole has to compensate it, right? So now you can see that with many more ions, I can add many more holes. So the on-off ratio, so from non-conducting to conducting, or the other way around, is going to be much, much higher than for this only tiny electric double layer in the field effect transistor. So how does it look like in a device? So this is the channel. This is the electrolyte, and you can see here the channel is basically separated between two electrodes, source and drain, and you have a gate electrode that's immersed in the electrolyte. Now, if I put a voltage on the gate electrode, I can start pushing ions into the channel. Then ions have to be compensated by the holes from the source and drain electrode, which then make the current be larger or less large. So these OECTs are actually been around for quite some time, and people use them for transistors, for sensors, or even small circuits. And when we started working on it, we wanted to take inspiration from the first neuromorphic systems that Pascal had shown, but kind of modify them in a bit that we get some long-term potentiation. Now, I'd like to show this artistic representation of this system that we made, because it kind of looks like this synapse on the right. So basically you have these two polymer layers on both sides, and what we want to do is now to start shuffling ions from one polymer layer through the electrolyte in the other polymer layer. So this is how it works. We have two p-dot PSS, so this is the mixed conducting polymer again, so p-dot PSS is a conducting polymer, and it's separated by an electrolyte. Now this electrolyte does allow, obviously, ions to go through, but it does not allow electrons or holes to go through. It's kind of like a battery, right? So in a battery, you also have two electrodes separated by an electrolyte, and you can shuffle ions from one side to the other, and then the electric current has to compensate in the outer electric circuit. So this is also what we've shown here, that if we start pushing ions from one p-dot electrode into the other p-dot electrode, and then we open this gate here, basically charging the battery and then releasing the load, you can see that there's going to be a huge energy barrier for ions to get out of this again. They're basically trapped. And this is very analogous to charging a battery and putting it on your desk, right? So it doesn't lose charge, not much at least, if you put it on your desk. So this is basically it. You basically have a tiny polymer battery, and if you then start measuring the conduction of this thing, which again, as I showed you, is dependent on how much ions are there, you can nicely shuffle the conduction in an analog fashion. And that's what I've shown here. If you zoom in here, you see all the different individual conductance states that we can reach. Now, for the chemists among us, we had to add this PI, and I'll come back to that a bit later, for stability, and that basically means that we're shuffling protons that protonate this imine. The imine then blocks the negative charge of the PSS, and then you have to remove this hole on the backbone here. So basically, you go from a conducting p-dot to a non-conducting p-dot when you add this proton here. Now, if you think about synaptic weight change in a neural network, because that's what this device will be, you don't want to have this sawtooth behavior, but fortunately, if you optimize a little bit, you can actually get nice linear symmetric tuning as well. But I'll come back to that a bit later. So again, this, just as a reminder, this tuning of this analog device is what we actually need as a single part of this array, right? So you kind of want to be able to tune your synaptic weight of your neural network in an analog fashion, and that's what we're going to do with these devices. So this is one of these parts of this crossbar array. So the beauty of organic materials using polymers and electrolyte is that it's very efficient. You can already imagine if I have a polymer that is soaked in water, there's ions in the electrolyte already, pushing one ion into this film and then displacing a hole is going to be a very efficient process, right? It's just shuffling ions in and out. What we did in this graph is basically show that each making the device area smaller and smaller, you can see that there's some kind of linear trend. And you can already go to some expectation for a 1 micrometer square device. You're going to have to switch with 55 femtojoule only. And this is very much compatible with how a synaptic event happens in the brain too. So the first thing that we wanted to show is to do some learning. And learning, this is analogous to what you want to do in neuromorphic systems, right? So you want to train or teach a certain network to recognize something or to associate something. And the simplest learning experiment that you can do is the Pavlovian dog. And I'm sure people have heard about it, but the idea is that if a dog sees a bowl of food, it starts to salivate. If it sees a bell, it doesn't do anything. But if every time you give it a bowl of food, you ring the bell, it starts salivating. And the next time it hears the bell, it thinks, hey, there's going to be food. So I'm going to start salivating again. It's called associative learning. And what we basically did is to try to link two inputs, so food and bell, through these neuromorphic devices to basically make sure that if there's going to be a bell only, it salivates too. And that's what we did here. And you can see here, if we probe the side of food, there's going to be a signal. If you probe the bell, there's almost nothing. Then you start tuning this connection strength between the two. And at some point, if you do only the bell, you also have a signal. Obviously, this is a circuit analogy of this system, but at least it shows that you can link the two things together. Now, this is all very nice. And the nice thing about organics, as I said, is that you can nicely tune in an analog fashion. And people have been doing neuromorphic computing or neuromorphic systems with memristors for a while now. And they don't have this beautiful intermediate resistance states in an analog fashion. But what they do have is once they program their system or device to a certain level, it stays there, right? And what you can see in this graph is that if we just use a p-dot device and you measure the conduction coming from this level and measure the conduction from this level, you see that already the conduction goes up very quickly, right? So you kind of, what we call in the field, you kind of lose or you don't remember your state anymore, your conductance state. Even though we open this gate, right? So you store the battery to a certain level, still it loses its information. And this is because p-dot doesn't like to be reduced, right? It likes to be oxidized. It likes to be conductive. And you can see that in this graph where we show what the oxidized p-dot, so the normal p-dot, the change in conduction over the normal conduction after some time, 5 minutes is, and you see that the reduced p-dot, so that's this part here, after 5 minutes, the change is much, much higher, right? So what we did, the first paper was to add this amine vapor, as I showed you before. So basically you tune this p-dot to a non-conductive state, it turns nicely dark blue, and then it's much more stable. And here you can see that the change again of conduction after 5 minutes, if you add the PI, is very nice, so you have a much better stability here. But then we saw that the conduction on the other side is now much less. So this means somehow even though we add this PI to make it stable, on this side when it's again oxidized, it's not stable anymore. And this is what we believe is because that side is susceptible to diffusion. What I mean with that is that if you have the amine in this on this side, you have the amine positive, it nicely links with the PSS negative. But on this side, obviously the p-dot is going to be conductive, so the p-dot is going to be positive, and then this amine is not positive anymore. It's neutral, and neutral in water can just dissolve and diffuse out. So that's what we believe is happening. So what is then the solution? The solution is that we added a Nephion layer, so not a liquid electrolyte anymore, but a salt electrolyte, and we encapsulate it to prevent oxygen. So this is what you can see here, that this dark blue line you have on both sides, you have the p-dot, so the system not be much stabler than before. So operate an oxygen-free environment and use a solid-state electrolyte. And here you can see that long-term retention is still not amazing, on the outskirts of the device, but it's much, much better. Then another thing is, obviously we have an analog tunable device, but you can also think about how many states do you actually need for a stable neuromorphic system to be trained. Now, generally, people think it's about 100, so that's why we measured 100. But you can also think about this in a certain, how do you say? You can also think about this in a certain way that the number of the range that you want to use in this, in this part. So here you see this is a very nice linear range, right? But if I go much higher, it's going to be less linear. So you have a trade-off between linearity and maximum range. And that's what I try to show in this graph. So the range that you want to use determines the linearity, but it also determines how many states you can use. But then how long these states have their retention depends on how many states you define as well, right? So here you have a nice overview of, okay, if I have only a couple of states that have to have a very high range, then the retention is going to be only, so if I have more than 100 states, the retention is going to be very low. But if I only define 10 states for a 90% of the range, the retention is going to be very high. Now, if you add noise, which obviously our device is going to have, you have this graph. So you really see that you have to play around a bit with what is the number of states that you actually need and what is the retention that you need for that. Now, as I showed you, we started this system with PI vapor, and you can imagine a vapor deposition process is not as controllable, right? Especially if you first make your devices and then you start to add your amines. It depends on how long you do this process. It's very difficult to control. So at that point, we started working with the chemistry department here in Eindhoven, and we figured, what if we start adding these amines to the solution already? Now, we obviously first started with, we tried with polyethylene amine, PI, but that actually crashes out immediately in the solution. So then Tom and Scott came with the idea of trying different small molecule amines and starting to dedope it with that. So they changed the different concentrations, spin coated the device, and then heated and built the device. So these are the three amines that they investigated: diethylatriamine, DEMTA, and TAEA. And they all have their different properties, but the important thing is that once you put them in solution, they don't immediately react with the pedal. They actually need some energy, some heat to start this reaction. Otherwise, you cannot spin coat it anymore. So they made devices from that, and again used it in a certain OCT transistor sensor setup with a source and drain to measure the conduction of the channel, and then the gate to push in the ions into this channel. And you can see here in this graph that we actually moved the pristine device, or the normal PDOT, into a dedoped PDOT here, and you actually have this threshold voltage that's almost around 0. So you really have a device that's now normally off instead of normally on. And for each of these concentrations, for each of these materials, you can see that they're almost all, a couple of them, are very nicely enhancement mode devices. Now, why is this important? Well, you can imagine PDOT is a very conductive material. If I make a huge array of PDOT devices, that means, let's say I have thousands of them. If they all draw a little bit of current and you add thousands of those currents, it's going to draw a lot of current and it's going to heat up the system. So you kind of want to have a system that you can turn off, basically turn it into an almost non-conducting polymer anymore, and then tiny bits turning it on. Now, the nice thing about these materials is that they're very stable. This is 1,000 cycles. You can see between the first and the 1,000, almost no degradation takes place. It's also nice to use them as in the neuromorphic system, so you can see that we can nicely linearly tune this conduction again. That's for PDOT, and as I said, you want to basically tune the PDOT off so that you can use it as a neuromorphic device. And that's when we started working with Groningen, and they had this donor acceptor molecule. And the nice thing about this one, it's a semiconducting polymer. So it's basically already completely off when you work with it, when you start with it, and then you add the ions to turn it a little bit on. Now, this polymer doesn't really like water in the normal sense, so that's why the chemists had to add these ethylene glycol side chains to make them more susceptible to water, so that the ions can go close and then push away or add the electron or the hole. Now, because this is a donor acceptor molecule, you can see that it works both in p-type as well as in n-type. And this is very surprising to us because n-type generally is not very stable. I mean, you see some degradation here over time, but still there's 3 orders of magnitude on-off ratio for the n-type. And this means actually that this system can be used as a ambipolar material, ambipolar transistor material as well. And as an electrolyte here, we use a solid electrode based on an ion gel, an ionic liquid, and this polymer matrix. And that actually works very well. So if you want to build large computing systems, again, you kind of don't want to have a liquid electrolyte, of course. And also in the neuromorphic system, so in tuning the weights, you can see here, we can nicely analogically change this system as well. Retention itself is not that great, unfortunately, and we have to operate it in nitrogen. The downside of these semiconductor polymers generally is that they're very susceptible to oxygen, so they're very sensitive. But obviously, if you use nice encapsulation techniques, you can overcome this. So now let's go to this neuromorphic array. We want to basically use, again, this chip where each of these nodes is going to be part of a layer of a neural network, and you want to change all these nodes to a certain level. Now, each of these nodes is this single neuromorphic device. You can shuffle your ions from one side here, you can tune the conduction here, and then you have your weight of your neural network. Now, there's a couple of challenges in this system. So first, you have, let's say I want to program this guy, or in this case, I want to program this guy, I put a voltage here and a voltage here. The difference between that is going to be the one to tune it, and that worked well for this one. But you also can see that it's going to be half selected. So if you put 0 volt here and 0 volt here, still this one will see half a volt and this one will see half a volt. So half select, undesired partial programming. At the same time, you also have sneak currents. Let's say I want to write only this guy to a certain new level. There's also going to be currents going through here, 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 and then here. So you have all these different sneak paths that you also don't want to have. Now, there's different ways of doing that. You can add access devices, and our colleagues at SEMD came up with this idea to basically add this memristor that only operates, that only allows a current if there's voltage higher than the threshold voltage, and then program our PDOT devices. So you can see that you can nicely only program parts of this system. That's very nice, but it still requires another layer of memristors on top of our array of OCTs, right? So what we came up with is the following. So we have, again, our source drain channel here. We have the gate, and if you zoom in here, we separate the gate from the channel using this femtosecond laser. That's a very high frequency laser that doesn't produce any heat. So you really evaporate your whole thing here and nicely separate the drain from the gate. And then we use polydopamine as an electrolyte. And the reason for that is, well, first of all, it's nice and flexible because it's a polymer too. But the other thing is that it's actually a very bad proton conductor. It works as a proton conductor, but because it's so bad, it needs kind of high energy for protons to move in and out. So you need to overcome this barrier of the PDA, polydopamine, for a proton to go into the channel. Now, once it's there, it cannot really get out anymore because it has to get over this barrier too. So here you see that we can nicely tune the conduction of our system similar to before, but now we don't have to have this opening of the gate. So we really only do programming with a closed 0 voltage gate after the program. And we show that we have some good retention too. So this is about the materials, the devices, and I would like to go to the next point because obviously organics are nice for lab work. We can nicely, easily spin code them and build them, but they also have some advantages beyond just demonstration in the lab. And I would like to highlight them here. So the first example I would like to present is together with one of our panelists today, Pascalis Goupedinas at Max Planck Institute. And our student Imke has shown that we can add to this Lego robot that we bought. We can add this neuromorphic organic mini brain. And why we want to do that is because we want to teach this robot how to solve this maze. Now, this maze is a honeycomb structure, and on this Lego robot, there's already a sensor that actually follows the line of this maze here. But once it comes to a cross point, it has to make a decision: go left or go right. What we want to teach the robot is that if it sees this navigation cue, it turns a certain way. If it takes a wrong decision, it will anyway end up to the end of this maze. It will bump its nose here, that's a pressure sensor. It will bump its nose into the wall and basically gets punished for taking the wrong decision. So how does it work in practice? So we have two devices. We have a neuromorphic device where we can change the conduction in a non-volatile way, so in a permanent way. And we have an OCT that changes the conduction only for a little while, right? So basically, this is a volatile device. Now, if you put a voltage between here and here, you get this voltage divider, and the VM basically determines what the chance is of turning left or right. Now, the idea is that if you see a certain, if they see the navigation cue, you get this little spike here. So at 60 seconds, it sees a navigation cue. And depending on the ratio between the OCT and the neuromorphic device, the spike also becomes larger and larger. At some point, it crosses a threshold so that it actually turns always the right way. So schematically, that looks something like this. The reflectance sensor sees the navigation cue, gives you this spike here. The touch sensor actually gradually changes the memristor device here, and thereby also changes the peak height of this signal. So basically, the VM at the beginning is a small peak. At the end, it's a very high peak. Before training, it does everything randomly. After training, it makes a correct decision. So this is how it looks like over time. Imke did many experiments and measured this robot, and you can see every time it's getting a little bit further into the maze. And also you see the navigation cues determine the path, but obviously it's not learning this path. You can also put the cues somewhere else and it can still follow this. It learns how to interpret the cue and thus make a decision after that. So the next thing that we can do with organic materials is we can use them for on-chip learning. So the nice thing is that because the devices are low power, they're easy to tune, we don't need large-scale computers, we don't need external power supplies, etc. We can just make a small chip where we have this neuromorphic array, this neural network on chip that we can train and that we can also retrain. So in this project, what we try to show is that we can actually make a modular neuromorphic chip, where on the one hand you have a sensor input, could be anything. In our case, it's an ion sensor, but could also be other things. You have the neural network that you train, and then you have the output that gives you the classification. Now, as an example, we wanted to measure or classify the disease cystic fibrosis. And the idea is that cystic fibrosis, you can kind of already measure by measuring the chlorine content. If that concentration in your sweat is high, you kind of have this, you have a high chance of having this disease. So just to emphasize, our goal is not to make the best cystic fibrosis sensor. Our goal is to show that if you have a sensor with a neural network in it, you can train it to recognize any disease as long as you give it labeled data. So what we do is we label the sweat for a healthy and disease specimens, we put them on the sensor module, it goes through the neural network, it gives you an answer whether it was healthy or not healthy. If it's correct, you don't do anything. If it's wrong, you start updating the weights. Now, this is exactly how any neural network works, right? So you give it an image of a dog. If it says it's a cat, you have to update the network until it's correct again. So this is what we try to emulate, but instead of doing this all in software, again, we all do it in hardware. And kind of what you want to do graphically, you want to separate this chlorine signal from the potassium signals. Now, I draw a neural network here. In practice, it's a single layer perceptron. So it's basically a neural network with only one layer and a binary output, yes or no. Is it diseased or not diseased? The sensors give a voltage output that goes through the weight, which is in our case the ECRM here, the 3 devices, that turn it into current. The currents, as I said before, you can sum. If the summation of the currents is high enough, it says yes, it's diseased. If it's low, it's not diseased. Here you see the conduction tuning of the 3 weights that we have, so it's more or less linear in a certain range. So how does it work? We ask, again, we give a labeled data, so we put it in the system. The chlorine goes through the channel of the device, gives a current, etc. For the potassium and the bias, if it's correct, nothing happens. If it's incorrect, you get an output of the error, which is the incorrect output, times the sensor input that was involved, which are all of them. You do a multiplication of those, and you get a voltage output that tunes a little bit, depending on your learning rate, a little bit the weight of this guy. So how does it look? Again, here we have the system, and here you see that the weights, all 3 of them, so the chlorine, potassium, the bias weight, over time. And each time you see a dark gray column, it means there was an incorrect output. So it gave an incorrect prediction, and then the weights are tuned a little bit. And you can see over time the weights are changing and changing until at some point they have a certain value that doesn't change anymore. And you always have the correct output. And graphically, you can also see that these lines start to separate more and more, and at some point it's a separation that's always correct. So the chlorine is separated. But because it's on chip and so easy to train these weights, we can actually retrain the system. With retraining, I mean you can add other sensor inputs. Now, the easiest for us was just to reconnect the same sensors, but now to the other inputs. So the weights now are incorrect again, but after a few trainings, you can already see it start to be correct again. But you can also retrain them into an AND gate or a NOR gate. You can nicely see over time that the weights get this value that it's needed. So this is very nice. We can show that organic materials are easy to tune and thus can be used in on-chip learning devices. So the final part of my talk will be about biointerfacing and neuromodulation. Because the nice thing about organic materials is that they're actually, some of them are biocompatible. They, as I showed you, they work with ions. And that's actually nice because the body also works with ions, right? And in the previous example, I also showed this ion sensor. So it's really a nice way to work with these materials. So the first thing I want to show is this device that we made based on this ambipolar material. If you remember, we had this new polymer that actually works in both p-type and n-type. And if you're a little bit of an electrical engineer, you can understand that if you have a p and n-type, you can make an inverter. Now, an inverter is not something new, and that's very, very common to do. But what we tried to do in this case was to add a neuromorphic device before the inverter. Basically, what you will do with that, if you change the resistance of this guy, the inverter will perform worse. Now, why would you want to do that? Well, there could be, if you do adaptive sensing, so if you do things on the body, you can measure things from the body like ECG signals or EMG signals, and not all of them are the same order of magnitude, right? In this case, for instance, what we show is that if you want to measure 2 different signals from an EMG, so in this case, the hand like this or a fist, what happens is that you have to look at the envelope to classify these 2 things. But if I amplify my raw signal from millivolts to volt using this inverter and I do the same for this signal using the same inverter, it gets out of the range of this inverter. So it kind of had your envelope signal becomes distorted. So at that point, what you want to do is to reduce a little bit the amplification so that the envelope remains and you can still classify these things. So there's other ways or other types of combinations of signals in the body that you might want to use to combine. But for that, basically, you change the conduction of your neuromorphic device here, and in that way, you change your gain of your inverter from here to here, so you can get a very low gain or very high gain. At the same time, we showed that if you build a large array of these systems, you can nicely also classify ECG signals, so heart rhythm signals, with a relatively high accuracy. So here, after a couple of training epochs, our hardware-based ANNs, if we would build something with this amount of neuromorphic devices, would be accurate in almost 80% of the signals to classify. So that's all very nice, but one of the nice things about these PDOT devices too is that because they're biocompatible, we can add actual cells on top of them. And this is what we did in this project, where we had neuron-like cells that released the neurotransmitter dopamine, and we placed them on top of this PDOT device. So this device is the same here, but now we have a side gate. And the nice thing about dopamine is that if you put a, let's say, small enough gate voltage of around 200 millivolts, it actually oxidizes and you get 2 protons and 2 electrons. Now, if you remember from the start of the talk, 2 protons actually can dope the PDOT and change the conduction a little bit. Right? This is how we actually tune our device in general. So we did that. We put many of these cells in green, you can see them here, on top of these neuromorphic devices with a microfluidic channel, and we started to pulse on the gate. Now, what happens in this system, again, is that if I put a voltage on the gate, I push in some ions into the channel, so I change the conduction of the PDOT. But if I then release the gate, it should actually go back to the original state, because there's no permanent tuning. That's what's shown here in the control. You always go back to the original state. So the volatile short-term plasticity, basically. But because there's dopamine there that is oxidized, that gives protons and electrons, we get this permanent depression. So now, even though we don't open the gate again of our device, we still have this change in conduction. And this actually depends on how much dopamine is there. You can see in this graph, the more dopamine we put, the higher this change in conduction is. So the nice thing here is what I want to highlight, that instead of just measuring the electrical activity, as I showed you at the beginning of the talk, everyone always measures only electrical activity. We can not only measure the chemical surrounding of these neurons, but we can also store that locally. So you can have a historical memorization of how much dopamine was around this device over time. And that's actually very useful if you want to build things like adaptive prosthetics or adaptive brain-machine interfaces. So we actually have this first artificial chemical synapse that we can tune not with electrical signals, but also with the neurotransmitters. Now you might ask, sure, you can only depress this device, you can only tune it one way. That's true. But because of the microfluidics, we can actually emulate something like something that's called exocytosis and endocytosis. Basically, by having a low flow rate, you tune your device with the manner I said. If you have a high flow rate, basically you flow a lot of oxygen that then oxidizes the PDOT again. You get back to your original conduction. Now, until now, I've shown that everything we did in our system, in our neuromorphic devices, in our materials, is a quasi-static change of the conduction. Now, you want to do this change in conduction because this is how you tune a neural network. This is also how you might tune the input-output for robotics. But in fact, the body works more with spikes. with action potentials, and it's not a static tuning of your system. So what we try to emulate in this work is to recreate a neuronal pathway. Now, a neuronal pathway from, in this case, a light receptor, so your eye, basically your retina, changes the light into a certain frequency of pulses. Depending on how much light there is, you get a higher frequency. And then from this afferent neuron that is at the outside of your body, it actually tunes this signal more and more depending on how much neurotransmitters are available. So the interneurons talk to each other with these synapses, and the strength of these synapses is actually regulated by the neurotransmitter environment. Now, this is what we want to emulate, and of course, there's been a very nice work on organic artificial neurons before, and I highlight two of these examples here where they really look at the potassium and the sodium channel to really emulate the shape of the spikes and to get this dependent on the concentration of ions, etc. So our goal in this project is not really to emulate or to make a better neuron, but to really start emulating the pathway from output of the light or the pressure, etc., into a longer cascading system. So we can do the sensory coding from a optical sensor into spikes, and we want to then translate these neural spikes into different strength to also tune the output of your neuron. So really get this neuronal pathway. So the first thing is relatively simple. You go from how much light output will be a voltage. The voltage actually determines in the spiking circuit how much what the frequency of the spikes is. So you have a higher voltage output, you have a higher frequency. The modulation itself works with this dopamine synapse. So this is the chemical synapse I showed you before. If we tune the weight of this chemical synapse, it actually tunes the frequency from the frequency coupling from the input to the output spiking circuit. So you can see from gray to red, we can increase the frequency if we increase the synaptic strength. Again, this synaptic strength is not done electrically. We don't tune this weight electrically. We tune it in a chemical way with dopamine. And then if we take this one step further, we can also have signals that are spikes that are not there, and that can only appear if there's dopamine around or if there's serotonin around. And that works something like this, where basically you have an input spikes, and then we have the dopamine synapse, so in between here, that actually starts tuning up. So at some point it reaches a threshold, and at that point, the next neuron starts to spike. You see here, the red one starts to spike. Now, the serotonin synapse is related to that. So only if there's been dopamine here and there's serotonin here, we get the blue spikes. If there was no dopamine and there's PBS later, we get some spikes, but we die out. And the same if there's only PBS in the first one, there's no spikes at all. So here there's really a cascading, triggering neural pathway. While at the same time, we can also modulate this into a artificial retina-like system where there's always persistent spiking neurons, and the spiking neurons frequency between the two actually depends on the dopamine, so the connection strength, so the chemical synapse, as well as the serotonin synapse. So you can see the frequency increases for that. And of course, this also depends on how much light there was. So I come to the end of my talk. I hope I explained to you that our organic materials, our neuromorphic organic P.PSS mixed conducting polymers, are actually very nice in the field of neuromorphic engineering. They have ideal properties. They can work in low power. They are easy to tune. You can easily integrate them on chips or on standalone autonomous robots and that walk around on battery power. You can use them for on-chip learning and retraining in biosensors. And because they are biocompatible, we can also use them in artificial neuronal pathways and at the interface with biology. So I'd like to highlight a little bit one slide of our nice special issue we have in this Materials Horizon journal that you can still submit to if you are very fast. And I'd like to thank everyone from my university that worked on this work, so my students, but also the collaborators at the other universities, the funding agencies, and of course you for your attention.
Yeah, thank you very much, Yoeri, for the excellent talk. Let me now also start sharing the screen from my side. Yeah. No, thanks a lot. So then I will now introduce the other panel members, after which we will start the panel discussion. So I will start with introducing Hans Kleeman from the Technische Universität Dresden. He got his diploma in physics from the University of Jena in 2009. And then for 3 years, he joined the group of Leo at the Technical University of Dresden, where he focused on organic electronics. Hans also had a joint collaboration with Nevolet Samsung as a research or project leader on organics transistor applications. And afterwards, he returned to academia in a group of Feng Wang, physics department of Berkeley. He has also quite a few prizes and a lot of papers in the top journals. But maybe the last thing I would like to highlight is that he also got his habilitation in 2021. Then let me introduce the next panelist, Pascalis Coupedenes from the Max Planck Institute of Polymer Research. He got his PhD from material science from NCRS Demokritos, Athens, Greece in 2014. After that, he started his during his PhD, he focused on ion transport mechanisms of organic electrolytes for non-volatile memory applications. Then he was a postdoc in the Department of Bioelectronics in France, where he focused on organic neuromorphic devices. In 2017, he joined the Max Planck Institute for Polymer Research in Germany, where he is currently a group leader on organic neuromorphic electronics. And then our challenger is Pai Zhang from Eindhoven University of Technology. She received a PhD degree in chemical engineering from the chemistry department of Eindhoven University just very recently, 2023. Then he joined the neuromorphic engineering group of Yoeri at the same university as a postdoctoral researcher. She's currently focusing on neuromorphic systems to integrate memory and learning functionalities in responsive materials. So I would like now to start the panel discussion, and I think it is the nicest to start with the youngest panel member, with Pai Zhang. So maybe you can open a discussion.
Yeah, that would be great. So thank you first, Yoeri, for the wonderful talk. And I want to ask you several questions to challenge you. So maybe I can start with the device fabrication. So first one, not only me, also other colleagues, they experience this device-to-device variability. And that means like when you prepare a different device, then the property might be slightly different. And this might not be very ideal for the application. So my question is, yeah, what's the cause do you think is for this variability, and what do you think, how can we overcome it?
Yeah, that's a very good question, Pai, and thanks for being here. So yes, organics always have their difficulties in variability. So this is one of the challenges that these systems always have and probably always will have. Especially if you reduce the size of, for instance, P dot, you get into the morphology regions where you might have P dot rich or P dot or PSS rich regions. It's usually different in conductance. Now, the nice thing about neuromorphic systems is that we don't really care too much. As long as as I showed you in the slides too, as long as we are more or less in the same range, we can get away with not being the same exactly, because this is a neural network that's trained that you can always get around of small imperfections. In fact, sometimes it's actually nice if there's some imperfections. So yes, we need some kind of overlapping regions to make sure that the weights can be mapped to the conductances, but it doesn't necessarily have to be as strict as, for instance, for normal transistor, silicon transistor, etc. They have a much higher requirement for these kind of system, for these kind of applications. So we can actually get away with pretty large device-to-device variations for now.
Yeah, that's good to know. So
also, maybe I can jump in here and say something about that, just to add on what Yoeri said. I think it's not only we get away with less reliability, but it's actually a feature that we have, because there are many algorithms in neuromorphic computing that need stochasticity, they need noise, and then they become most efficient. So neurons, for example, often spike stochastically. So we need these, let's say, low variability. So it's more like really a feature than a bug.
But then my question is, will that be predictable, like the noise, because the device variability, that's not something we can predict. Will that influence for the algorithm?
So the noise is not predictable in this case. So the spiking will remain stochastic. And this is really necessary that you have a decoherence of neural spiking, but they become coherent if they have a certain timing, and then you create a wave of spikes.
So we assume like the variability can be the noise, which is good in some way.
Yes, absolutely.
Yeah.
I want to ask another question about the device application. Because in some application we want a very complex neural network. So in that sense, we want a larger neuromorphic arrays. So as usual in your slides, or what I also see from other papers, normally the arrays is often limited to 3x3 or sometimes 3x4. And I'm wondering, like, why is this? It's not that big at this moment, and yeah, is there any limitations? And what do you think? How can we deal with that?
That's a very good question, because it is. There's a couple of reasons. So first of all, it's not easy to build large arrays, and even if you can, it's not easy to operate them predictably. So what we generally try to do in our labs, and I speak for the other panelists too, is to showcase proof of principles to make sure that we can actually show that things work, so that other people who have a better labs or better equipped with making large scale things can take over these concepts. Now, that's one of the reasons why we generally limit ourselves to small things. At the same time, also, I showed you that the devices that we use for now, especially the polymers, they're still pretty conductive. If you scale them up to 1,000 by 1,000 devices, you're going to draw a lot of current, and it's going to heat up the system pretty quickly. So you really need very controlled, very tiny devices that only uses a little bit of current, that have very high resistance. You get into problems of how to reach the middle device in a crossbar array, because you also have, if you make them smaller, you also have wire resistance, you have capacitive effects. These are all technological issues that big companies like Intel or Samsung are much better equipped at solving. They have much more experience for that. So what we try to do, or at least I try to do, is to show things that we can do already that are useful. For instance, this small biosensor. I mean, it's a useful application, even though you can buy a much better cystic fibrosis sensor just online. It's showing that this concept of training works well if you have an easy to tune system. Obviously, if you want to do an image recognition on a chip, you need much larger things. But at that point, our lab is not sufficient for that. We don't have this experience also for making these systems. So in general, there's no limitation per se why people always show these small arrays. It's just a technological challenge to do.
Yeah.
In which, if I'm allowed to comment on something here, in which, again, I agree with Yoeri that industry and industrial environment is much more well equipped, to upscale a technology basically. But what I want to add here is that there are many application domains that upscaling is not important. For example, in sensors, in biointerfaces, talking about some hundreds of devices, it's more than enough for many applications.
Yeah, I see. So we can just focus on the thing we can do with the small array, and yeah, and then later if we can make a bigger devices, then focus on something else that we can do.
So maybe I can also add a thought on that. I think the challenge does not only come from the organic side, where we have to make the system always bigger, but it also comes from the silicon side, because it's wishful thinking that we make everything out of organics. There needs to be an interface to silicon. And silicon also has to learn how to make this kind of hetero integration with different kinds of materials, with sensors, and so on and so forth. Because this is also where silicon is very weak at the moment to make efficient edge devices. They're very good at making large-scale processors, but connecting them with hundreds of sensors, that's a big challenge. And I think this is exactly the interface where both worlds have to come together, organics as well as silicon.
Yeah,
and we know from experience, it's not easy to convince silicon people, but if they come together like the OLED community at some point, if they want to, we can make it work. So I also believe that indeed, we are good at some things like on edge sending things, and we at some point we indeed need to, and this is a very good point by Hans, we cannot get away with making PCB systems anymore. We need to integrate with large scale silicon CMOS and circuits as well.
But I think that is timely. I think some big companies are already changing and opening up much more for molecular materials. My favorite example, or one of the favorites, is Samsung with the foldable phones and organic light emitting displays. I think they are quite far advanced already with being open for molecular materials. So many more still to follow.
Exactly.
On that, I have another question. Like, is there any other big challenges by combining these two fields, like the organic neuromorphic thing, and then also the traditional electronics? Is there any big challenge? I assume there might be, and what are they?
Yeah, okay. I think there's many. Maybe I can highlight a few. I guess fabrication. The big silicon labs don't really like organic systems in their fabs. Temperature-wise, they use generally very high temperatures if they process their system. So organics are not really used good for that. But also indeed speaking to each other. So speed of operation for organics is slower, silicon is faster. You need to have an integration there. And I guess maybe just a people problem too, right? It's difficult to talk to people who have a usually different background that only publish in IEEE's journals, etc. So the fields are definitely just separated, and we really like Chris says nicely, we are getting there. We're getting into each other's zones, but still we're not there. So also a challenge in people and fields, I feel like.
And I think also there is maybe some in-between pathways possible. I think back end of line applications will make it much faster than frontline applications. So yeah,
and if they really want to, they can. I mean, it's always, you can always make sure that the last process step is the organic layer, etc. So it's just that it's not convenient, and then people the silicon people generally don't really. I don't want to say things I regret, but at least it's a difficult field that's already there forever, and that's it works very well and it's very impressive. So they tend to be a bit more conservative in. But I agree also with Chris that they are opening up and they can see the benefits of these materials and devices that we can bring.
And both sides still have a lot to learn from each other, basically, not for improving metrics necessarily, but adding new functionalities. This is really important for organics, adding completely new functionalities.
Yeah, I completely agree. So does that answer your questions?
Yeah, that's good answer. May I ask further questions?
Yeah, sure.
Like in the sense of application, like we can add more to the application sense. So I'm very interested in that. So for example, in software robotics, I'm wondering what's your opinion, what we can add in there, what we can use of this neuromorphic system for the soft robotic control. Can you give me some, suggestions?
Yeah, I mean, the nice thing about organics is their flexibility, right? So we are like Chris also mentioned, the flip phones, the closable screens, the foldable screens. So for soft robotics, for bio things, everything that can move, that can change, the organics are actually nice because they're flexible. You know, PDOT has been used in stretchable systems even. So you can even do electronic skin, and you can really do applications like this. So I think, yes, I mean, it's going to be tricky to put a silicon rigid chip on a body that can move, right? So for that, they need polymer, they need organics. So yes, also for soft robotics, the organics are actually very nice.
So maybe we can move on to the next panelist to give also that person some time to ask questions. So maybe we can move on to Hans.
Sure. So the one question that I would have to Yoeri, I mean, you told a very nice story going from the single device, how to evaluate the plasticity and so on and so forth, to the final application, the biosensing, etc. But the applications you have shown, for example, the neurons on the PDOT, this is like a very primitive system. So what do you think are the next steps we have to take in order to make a solid bio interface, also volatile? What is to be done on the material side as well as in sensing schemes?
That's a good question. I think it's that's the challenge. Yeah. So I guess, you know, getting from zero into a single device is already a big challenge, as you all know, and you do. But now the next step, making it into a functional system, requires a lot more, right? Because now you can not just link a single device to an output. You also have to link them together. You have to make sure that they talk to each other, that they can integrate with each other. I think material-wise, we should be relatively okay with the materials we have. They have a very high transconductance. They're very stable. You can measure things. You can functionalize PDOT to measure other things. But getting enough signals to combine the signals into something useful, and then doing something with that again, that's, I think, the next challenge. So really integration. I kind of links to the previous discussion we had. The integration at that point, as Pascal said, we also need to learn from the silicon people, like how to integrate, how to talk to bridge multiple things together and make a functional system from that. I think this is very much a challenge.
But I think my question comes more from the other side, so not from the silicon integration, but more from the biology integration. I mean, the PDOT might be a good interface for neurons, but not a general interface for all different kinds of cell cultures, right? So you need to have, let's say, intermediate materials between your organic electrochemical transistors and your cells. So something like gels, hydrogels, things like that. So I think that there's also a lot of work needed on this side, probably.
Yeah, I think you're absolutely right. So the cell experiments that I showed in the talk, I'm not an expert on that, but I remember they have to put certain layers in order for the cells not to die. They have to get some kind of extracellular matrix or some kind of a interface. I mean, anyway, the cells die a lot. It's very difficult to work with biological samples. So yes, there's a huge gap too with the biology, like the people. And maybe it's even a more conservative community, biologists and neuroscientists. So I guess there's also a huge gap there. But indeed, just putting cells on a 2D film, that's fine. You can do that, but that's definitely not how the body is working. You need the 3D environment so that the cells actually behave as they would. You need indeed hydrogels or extracellular kind of matrix system for them to feel natural, to behave as they would. And then still, how can you measure things inside of the cell culture and not from only the sides? So yeah, I agree. There's also a huge a gap there to improve on.
And then my second question is related to let's say the sensory input. I mean, you have also shown a couple of examples how to sense materials, and usually we are trying to make our sensor selective to certain species. But I think this is not how our nose, for example, works, or other, let's say, senses that we have as human beings. So what do you think? What is the strategy? Putting all the effort in designing the best sensing device, or making up our mind of how to use an AI-assisted system in order to distinguish between all the signals collected by one single sensor, which is like our nose. So where's the truth?
Yeah, it's another good question, Hans. I guess the truth is in the middle always, right? No, I think I only got into the cell research when we started working on this, and that's a huge field that's always about selectiveness, right? You cannot just get signals from everything at the same time and then you know everything, right? One example, for instance, if you have the two neurotransmitters, dopamine and serotonin, serotonin oxidizes at 300 millivolts, dopamine at 200. So if you put 300 millivolts and you have both neurotransmitters, you don't know which one you're measuring, right? It's only selective if you only use dopamine. Now, the same holds, I guess, with many normal sensors. So we had to put an ion selective membrane so that we can only measure potassium. If you don't do that, you measure potassium, calcium, sodium, etc. Now, I don't think you can actually use, maybe in some instances, yes, multiplexing or time differences by using certain frequencies, etc. You can start distinguishing between different ionic species without selective membrane. Or maybe some kind of AI algorithm can actually do that, but because there's difference in size and time difference, etc. But overall, it's very difficult measuring different species of, in this case, only ions. Right? It's not even any biological molecule even. It's just an ion. It's already very difficult to selectively measure these without selective membrane. So yes, maybe a combination of the two, or a combination of different types of sensing to distinguish between that. And yeah, I don't know how the brain actually does it, because it must be that some different molecules get accepted by different receptors in our nervous system in the nose too, right? It's not one receptor that measures everything. I don't think that's well, I don't know, but I speculate that it's very difficult.
Yeah, I think there are a couple of very precise and selective processes, but most of them are not really, right? And then there needs to be some AI or some neural network in our brain behind that able to select that. I think it's a
so you combine the two, indeed, very selective ones
think.
with
many phenomena. Sorry, Yoeri, please go.
No, go on.
Yeah. So many phenomena in biological systems basically break down in a convolution of those kind of phenomena, from simple things to more complex things. So olfactory system, I think, is the most complex thing, because you have thousands of receptors, and then they have to combine. Some of those receptors do similar things in order to recognize, the huge diversity in smells that we have. But still, if you go in simpler systems like, I don't know, pathological conditions. So in epilepsy, for example, we are just measuring with external electrodes the movement of ions, of many different ions, basically. But if you go down, I don't know, a couple of levels below that, you still have, I don't know, 2 or 3 different ions that they do the job. So it really, you really have to deconvolute your system. And some systems are more complex, some systems are less complex. But still, because probably from material science, we don't have infinite directions to synthesize every kind of receptor. Basically, we have to rely partially, at least, in algorithms. I guess this is the easiest intermediate way. I guess that's my guess.
We can build convolutional neural networks too, right? So it should solve something.
Whenever material science doesn't work, I mean, you still have the support from algorithms, of course.
Yeah.
These are very interesting concepts. Yeah, but maybe biology does a lot of things simultaneously and in a not perfect way. Like in our nose, I think it's not just one area, but a combination of factors. Even our tongue is very important in also smelling, but also tasting. So it's incredibly complicated. Yeah. But then nature can also do some things that always have fascinated me. So when we talk about smell, there is also things like pheromones. And some pheromones can be detected at a single molecule level. And even insects, so for instance, with just a few molecules, can even determine already the direction where it came from. So it's also fascinating to think about that. Out of so many molecules in air, you pick only one and you get a massive signal. That is really fascinating how that is done, right?
Yeah.
That would be fascinating if we could create that in our labs. Yeah.
Very big amplifications, I guess.
Yeah. Selective out of all the noise. Yeah. Hans, you have more questions?
Yeah, I've one. I mean, you talked a bit about the characterization of your synaptic devices or the memoristic devices, and said always, yeah, sometimes you have a quite good retention, sometimes not. And to be honest, this is always one big challenge we're also facing in our group. So we have devices that have responses on many different time domains, right? So they have a short-term plasticity, but long-term, basically it's a mess. They respond to everything in time domain. But I think this is a very big challenge for training, because the way we train a system, we always just use a learning rule at one specific time domain, and then we just training the system. I think that's also the way you've done for the backpropagation. And in order to advance to bigger systems, I think there is a very big need to develop also further models for the integration of these multi-time step, let's say, synaptic plasticity. But my question is basically, do you think there are good approaches in this direction? How are other people dealing with these issues?
Yeah, so it always depends on what you want to do with it, right? So indeed, in the systems like we did with Pascalis, we kind of need retention of at least tens of minutes, because otherwise the robot loses its memory, right?
Yeah.
But if you refresh, or you put in new data every 10 seconds, then you kind of don't really care that all the weights are moving a bit downwards, right? Because you refresh it anyway with a certain learning rate over time. And I think there's tricks if you need them to be longer retention than you can do this refreshing the memory. I think a couple of groups in Germany showed that you can just refresh the system every so many minutes to keep remembering. But then there's also tricks to if you reduce the on-off the range that you use. I showed that in a certain figure. If you reduce the range, you kind of have less of these retentions going to the middle, so you have a much more longer retention here. You can also go into systems where you tune your homo-lumo, or basically if it's an inorganic, your Fermi levels, so that they're always below the oxidation potential of oxygen. So you kind of don't really care about ambient things, but then your range is also a little bit lower. Encapsulation, I think for us it's a bit difficult in the lab, but the colleagues at MIT who work on these protonic devices in I think tungsten oxide, they always encapsulate their system, and they're very stable over time, and they're very easy to tune. So if you reduce the size, also you lose a little bit of your range, because you have less of the volume to push the ions in. So yeah, there's many different cons or aspects that you have to take into account. For some systems, you don't really care if they change the weight over time, like you said, stochasticity, or even forgetfulness might be a good thing. You get stuck in local minimas of your cost function, and if you forget a bit, then the next time you try a new data coming in, you're out of this local minima, and you can go to the global minimum. So there's also, there's no good or bad. It's just whatever you want to need, or you need to do, you find the system that works. But overall, indeed, for the systems I showed, we kind of want to have certain long-term retention, at least in the tens of minutes where you do your experiments.
Yeah. Okay.
No, thanks. Then let's move on to Pascalis, so you can also ask a couple of questions before we close up.
Yeah. Yeah. So it's a question basically for Yoeri, but also for all of you. I mean, Yoeri, the depth and the breadth, especially of your research, is impressive. I mean, from your presentation. So, which means that it requires basically the overview of many different disciplines. So, how you deal with interdisciplinarity, basically, when you define a project or in your everyday life, basically, when you conduct your research. This is also for our audience, basically.
I think it's a good point. So, and I hope that Chris and Hans will also agree with this bit. Interdisciplinarity or multidisciplinarity is a very difficult thing, but it's also a very natural thing, right? So you become expert in a certain thing because you do your master's or your PhD, and then you learn from a new field. And the beauty of this field, at least the neuromorphic or the organic electronic field, is that it kind of needs from everything a little bit, or sometimes a little bit more. You need the chemist to design your polymers. You need the computer scientist to help you design your algorithms. You need the electrical engineers to design the chip, the material science to optimize your material. What we do over time is we read papers, we review papers, we work on these systems we get from, we hire different students from different backgrounds, right? So chemists and material scientists and engineers, and they all teach us over time the things that we need to know for our field. We can never be an expert. I'm not a chemist. I know some things about chemistry. I'm not a electrical engineer. I know some electrical circuits now. So this is what happens over time. And I think it's also about your interest. So what you like to do, learn more, you'll read about, you'll figure out things, how they work. But it's also an issue with, like, it's not a typical way of doing research. Even though many people do it now, it's still very difficult getting funding in interdisciplinary research. Every time you propose something on a material science with a certain application, if there's a referee on this application, they probably kill your proposal because it's not a state-of-the-art application yet, right? So my experience, at least in that, is that you have to be patient. You hope that you work with the right people so you get the experience to continue on that. But it's, I think this is the way to go. No one can be on their own little chemistry or physics island anymore to advance the science in the status we are now. So we need interdisciplinary research, and it's not an easy task, but it's definitely a nice way to work in.
Very well said. Thank you, Yoeri. Yeah.
Do you agree, Hans?
So, Hans?
Yeah, I mean, in general, I think we all agree that often our students are much more deeper into the topic than we are when presenting that, right? They are the experts on that, and we're becoming more the generalists, and also have the freedom to look into different fields. And then you're also open to learn new things. And if you learn new things, also the learning curve is very steep, right? I think that's the freedom that you typically have as a PI, that you're the generalist, you can have the overview and talk to different people. And as you said, talking to people is the best thing to do. So science works by exchange.
And luckily, there are many ways to also establish networks of people and get those networks even funded. And then you can really do together as a team amazing things. And that is really the nice things about also this field of neuromorphic applications, basically. And it can be done in so many different ways, in so many different facets to look at. And I think we have seen an impressive amount of that today already. Yeah, so I think I look at the clock and it is already almost time. So if there are no more urgent questions.
May I?
Oh, you're a real challenger.
I have one general question, not really very scientific. It's a personal question for Yoeri. I see you often have very energetic when I meet you. Actually, I'm wondering, how do you sustain your motivation and how do you manage your energy to do so many things and to achieve so many projects? Can you tell something like that?
So okay, thanks for this compliment. I think it's exactly what Hans said. So it's the students that are the experts and that do all the amazing work that we are allowed to present. we have the overview. I'm very excited about the work we do because it's such a nice topic. It's very interdisciplinary. It's very at the forefront of science. But because I don't have to spend hours and hours in the lab, I have a lot of time free to spend with my family. I mean, this is Friday. Generally, I don't work on Friday, actually. I only work 4 days a week because I think one day with my kids is important. So maintaining a good work-life balance, I guess, is it always helps you be more fresh the next week to have new ideas. Sure, if you have to finish your PhD, you have to work lots of hours in the lab at the last year. That's fine. I also did that during my PhD. But at some point, you need to also realize that things are beyond the lab can also influence things in the lab, which is a good pleasure in life, and work-life balance always helps you a lot in being creative and keeping your energy for the next time. So that's at least my personal experience for, I don't know if everyone agrees, but still, this is how I keep my energy.
Yeah. But for instance, what drives me is just the curiosity. In this particular topic, I find it truly amazing how these things work. But then we talk here today a lot about brains, but single cell organisms can also learn. So learning rules can also be already material dependent. You don't need per se neurons. So then you get very basic questions I love to think about. What is learning? What is intelligence? How can we define it? How can we measure it? How can you quantify it? And when you start to think deeply about those kind of things, you will see it is actually not so straightforward. And then it becomes even more challenging to try to recreate it in your lab and to find applications for it. I think that is just something that keeps me going.
Yeah, but indeed, curiosity obviously drives us as scientists as a base. And I mean, I always love doing things that I do because it's such an interesting field that we're in, and we just want to know more. This is in our hearts, right? So, sure, you keep the energy by being amazed by the things that happen that you can do in your science.
Yeah, so I think this is a very good way to conclude today's iCANX talk by Yoeri. So let me then hand over a very important thing. So now I think you can see it, Yoeri, the iCANX certificate. Today's episode was already volume 100, number 70, so it's a quite honorable number. So congratulations and thank you. For your wonderful contribution. And of course, also all other panel members for a very nice discussion. I really enjoyed it a lot. So before we really close up, let me just make a few more announcements. So I would like to advertise next week's talk by Hongbo Sun from Tsinghua University, and he will be talking about micro nano photonics. And that is it then for today. So thank you all, and I wish you all a very nice weekend ahead. Bye-bye.
Thank you.
Thank you.
Bye-bye. Thank you.
Thanks, Hans. Thanks, Pascal.
Thank you. Thank you, everyone.
Yeah.
Thank
Beautiful
you.
talk.
造奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can。你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。Oh yeah, yeah, I can, you can， 你也能够像我一样飞越最高山岗。
祝你生日快乐！该吹蜡烛了，
来，我帮你。啊！
祝你生日快乐！
生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，
没新意。